Alright, so today we're going to talk about Taylor polynomials. But I want to make sure that you watch the video on Taylor series by 3 Blue, 1 Brown first. Make sure you watch that first. That video does a beautiful job of conveying the idea behind Taylor polynomials, and the animations are wonderful. I love that video. So be sure to watch that first. And then come back and finish this if you if you haven't watched that video first. But the idea behind Taylor polynomials is to find a polynomial function that approximates a non-polynomial function. So let me write that down. So we want to find a polynomial function that approximates a non-polynomial function. Non-polynomial function. Okay? Because polynomials are just much easier to work with, as you've probably experienced. So what I want to do is sort of go through a little slower as far as how he developed the concept first, and then I'll show you the final result, because I don't want you to think it's some sort of magical thing that I'm pulling out of thin air. It's just makes sense. So so first of all, let's find a linear polynomial of this form, c0 plus c1x, that approximates the function e to the x near x equals 0. So the idea first is just we want the two functions to match. You know, we want f of 0 to equal p of 0. Okay, so we want, when we put x equals 0 into the function, either one of these functions, we want to get the same result. So f of 0, if I put 0 into our function here for f of x, we get e to the 0, right? And e to the 0 is just 1. Now, when I put 0 into this p1 function, right, p1 of 0, I have this constant c0, and then the other part of this polynomial is just c1 times x. So c1 times 0, right? That's just 0. So we just get c0. And if we want these two functions to match, then c0 has to be equal to 1, right? So c0 equals 1. Okay, so now we have one of the constants, and then we want to find out what the other constant needs to be so that they match, right? So so we have the value of the function matching. Now we want the first derivative to match. So we want the slope of the function to be the same. So if we take the derivative of e to the x, we get e to the x. So that's nice, because then if we put in 0, right, to e to the x, we again get e to the 0, which is 1. And the derivative of our polynomial, p1 of x, is just going to be, the derivative of a constant is 0, and then the derivative of c1x is just c1, right? So this is telling us that c1 has to be equal to 1 as well. So if we want a linear polynomial that best fits this function e to the x, we have p1 of x is equal to 1 plus x. Just substituting in c0 and c1 into our linear polynomial form. Okay? So, you know, that seems awfully simplistic, right? But it does pretty well near 0. We can just approximate the function with this line, right? And if we wanted to see, okay, well, how well does it match? We could test a point like 0.1, and if we look at p1 at 0.1, and it's just 1 plus 0.1, so we get 1.1, right? And we can also take a look at what the function e to the x is at 0.1. So we get e to the 0.1, put that in your calculator, and you get 1.105171. And it keeps going from there, but we'll just deal with 6 digits after the decimal place for now. And so then if I look at the difference between the two, so if I look at f of 0.1 and I subtract p1 at 0.1 just to see how far we're off, we get 0.005171. Okay, so that's not too bad, right? That's, it depends on what you're using this approximation for, but it's less than a 0.5% error. So not too bad. But again, that's, for values near 0. So 0.1 isn't too far off from 0. So, but let's see if we can do better, right? Let's see if we can do this, see if we can find a quadratic that fits this function. Okay, so so again, we want the value of the function to match, right? So we want f of 0, which we already said was 1, e to the 1, right? Or e to the 0 is 1. And the value of the polynomial at 0 is going to be, right, I'm just going to put in 0 for x, so I'm just going to get c0, right? So what that's telling me then is that c0 equals 1, just like we got before, all right? So also we want the value of the derivative to match, right? Now we already said that the first derivative of e to the x is e to the x, all right? So f prime of 0 is e to the 0, which is again 1. And if we look at the derivative of the second order polynomial that we have here, we'll just do p prime of x, right? Okay, so the derivative of c0 is 0. The derivative of c1x is c1. And then the derivative of the next term gives us 2c2x. Okay, so if we put in 0, right, so that's p prime of 0 is just equal to c1. And so now we know that c1, if we want the value of the derivative to match at 0, then c1 has to be equal to 1. Now that's exactly what we got before, right? For the constant term and the linear term, we got the same constants. So that's good. And now if we want to find it, we're looking for a quadratic. So we also want the concavity of the polynomial function to match the concavity of the original function, this e to the x function. And we can do that by looking at the second derivative. So again, the second derivative is e to the x, right? So f double prime, right, second derivative at 0 is equal to e to the 0, which is equal to 1. Okay, and then the derivative of the polynomial, right, is just the derivative of the derivative, so we're going to get 2c2. Okay, which means that p double prime at 0 is equal to 2c2, and we want that to equal 1 so that it matches the second derivative of the function that we're trying to model, which is e to the x. So that tells us that c2 is equal to 1/2. All right, so now we have the value of the function matching, we have the slope matching, and now we have the concavity matching. And so our polynomial, our quadratic polynomial that approximates this function is 1 plus x plus 1/2 x squared. Okay, so how well does that match? How does that do a lot better than the other one? You would think so. But let's take a look at the values at 0.1, right? We're modeling around 0. So near 0, this should match pretty well. So let's take a look. So if I put in 0.1 into this polynomial, this quadratic polynomial that I just found, I'll get 1.105. And again, the value of the function, e to the x, at 0.1, we've already found that was approximately equal to 1.105171. So the difference between those two, just take the difference, P2 at 0.1, we get 0.000171. Okay, so it's better, right? So now if I look at the percent error, it's less than 0.02% error. Okay, so that's pretty good. All right. And we can keep going. We can keep going and add more and more terms. So now we have a linear, we have a quadratic approximation. Let's try a third order approximation. So I'm gonna have you pause the video here and try this yourself. So we've already really done. We've found we want the value of the function to match. We want the first derivatives to match. We want the second derivatives to match. We've already done that part. And all we're adding now is we want the third derivatives to match as well. So I'm going to pause and let you try this on your own, and you can come back. All right, so I've written out the solution for this one so you can check what you got. Really, if you look at it, these first three steps are basically the same. These are just the same as the other, as example 2. Example 2. Right? Those are just the same steps. I mean, we've got an extra term hanging on there, but when you plug in 0, that extra term goes away. And so we end up with the same constant values for those first 3 terms. And so then there's just this additional step of looking at the third derivative of each of the functions and making them match at 0. Okay, so we end up with a constant of 1/6 on the x cubed term. And then we can look at how well it matches at 0.1. And you can see that it's pretty darn good. So less than 0.0004% error in this case. All right, now I want to make sure that you understand that this is just sort of developing the concept. I'm going to show you a shortcut way to do this, just using a formula. But I just don't like throwing out formulas with no lead up, because math needs to make sense. Right? And I mean, I could just give you the formula and be like, well, where'd that come from? But that's all we're doing, is making the value of the function match at the point we're trying to model at, and then also making the first derivative, the second derivative, third derivative, and so on match. And those are called Taylor polynomials. So the formula that you will be able to use on your homework and the discussion questions that we're going to get to is just that a Taylor polynomial is just f of 0. Okay, so we're trying to model some function f of x, right? And now in the examples we just did, we're trying to model e to the x, but it doesn't matter what function we're trying to model, just any non-polynomial function. The first term is just going to be f of 0. And then we have plus the derivative at 0 times x. And then we're going to have the second derivative at 0 divided by 2 factorial, right? Because we had to take the derivative of that particular term several times x squared, right? And then the triple prime at 0 over 3 factorial times x cubed, and so on, right? Kind of get the pattern. So the general term is f, the nth derivative, at 0 of our function divided by n factorial times x to the n. Okay, so that's the Taylor polynomial of degree n, approximating the function near 0. Okay, so now we can actually just use that result and don't have to go through all those steps of of taking the derivative of the polynomial and the function and making them match, because we have a formula now. So let's try and apply that formula. So let's take a look at example 4. Now, again, it's e to the x, all right? So this is just what we did before, but let's, instead of doing it the long way, let's do it using the formula. And now we want to construct a polynomial of degree 7. All right, so we've done degrees 1, 2, and 3. Now we're going to do degree 7. All right, so what do we need? We need the value of the function at 0. We need the value of the function, the value of the derivative at 0, and so on. So now, well, we can just start with f of 0. F of 0 is equal to 1, right? Put in 0 to e to the x, and you get e to the 0, which is 1. All right, and then if we take a look at the derivatives of e to the x, e to the x is super simple, right? Because the derivative of e to the x is e to the x. So f prime of e to the x is equal to e to the x. And double prime, f double prime of e to the x is e to the x. Oops, I can't write it. Equals e to the x, and so on, right? We could just keep going. F triple prime of x is equal to e to the x, right? So and so on, okay? So that's telling us that f prime at 0 is e to the 0, which is 1. F double prime at 0 is also 1. And f triple prime, is it supposed to be triple prime? Right, third derivative of 0. I always wanted to put 0 here. 0 is equal to 1, and so on. So I don't really need to go and compute the 4th, 5th, 6th, and 7th derivatives because it's all going to be the same. All right, so now we'll use the formula we have above to construct the P7 of x, right? The 7th degree polynomial, Taylor polynomial for e to the x. So we're going to have 1, right? That's our f of 0, plus f prime at 0 times x. So I'm just going to write x. And then we have plus f double prime at 0 over 2 factorial. So 1 over 2 factorial, x squared. And then we're going to have 1 over 3 factorial times x cubed. Okay. And then we're going to have 1 over 4 factorial times x to the 4th, plus 1 over 5 factorial times x to the 5th, plus 1 over 6 factorial times x to the 6th, plus 1 over 7 factorial times x to the 7th. Right? So there's our 7th degree polynomial. And so e to the x is really nice because e to the derivative of e to the x is e to the x, and then e to the 0 is 1 for everything. So you can see that's why we have 1 in the numerator of all of these coefficients on each of the terms in the polynomial. Okay, now I didn't ask for this, but you can also look at the difference between, how well does this model the function at 0.1, right? We made it match exactly at 0, right? But so for values near 0, it should be close. And so if you put 0.1 into this polynomial, you get basically exactly to the precision of my calculator, you get exactly the same thing as you do when you put in e to the 0.1. So I'm sure there is some error, but given the precision of my calculator, maybe I should make a note of that. Given the precision of my calculator, it looks like 0, so it's very precise. Precision. Okay, right? Okay. So, one last thing. What if we want to model a function not near 0, but at some other point? We'll just say x equals a. We want to model the function near x equals a, where a could be 1 or 2 or 3 or pi over 6 or a square root of 7. But we just want to model the function at some other point. So what we're going to do is now write a polynomial in terms of x minus a instead of x. Okay, so now I'm going to step back and I'm going to do it the hard way first, and then I'll give you the formula. Okay, so but it's the same concept. We're just trying to get the value of the functions to match, and then the first derivatives to match, and second derivatives to match, and so on. So in this example 5, we're looking for a third degree polynomial that approximates e to the x. So again, e to the x is nice and easy. And we're looking for this third degree polynomial. But instead of writing it in terms of x and x squared and x cubed, we're going to write it x in terms of x minus 1. All right, and x minus 1 squared and x minus 1 cubed. And we're going to find these constants, the coefficients that go with it. All right, so we still know that f of 0 is, right, f of 0, because it's either the x, f of 0 is equal to 1, right? And then let's look at the first derivatives. Now we know the first derivative of e to the x is e to the x. So just like before, the second derivative is again e to the x, and so on. Triple prime of x equals e to the x, right? And we can keep going, but we only need a third degree polynomial, so that's plenty. So, and then now we're going to evaluate the function though at 1, because we want the values to match at 1. So the value of the derivative of e to the x at 1 is just e to the 1, so it's e. And the second derivative at 1 is e. And the third derivative at 1 is e. And so on. Of course, we don't really need any more than that. So now let's look at the derivative of this polynomial. All right, this polynomial P3, right? P3, let's look at, first of all, the derivative of this polynomial. Okay, so when we take the derivative of this polynomial, the derivative of C0 is just 0. And then the derivative of C1 times x minus 1 is just going to be C1, right? We could multiply it through, or you could think of it as using the chain rule. But it's just going to be C1. All right, and then we just keep going. So if we take the derivative of the next term, we're going to end up with 2C2 times x minus 1. Again, you can think about it as using the chain rule. And the derivative of the inside function, the inside function is x minus 1. The derivative of x minus 1 is just 1. All right, and then we'll get 3c3 times x minus 1 squared. Okay, so just taking the derivative of that polynomial. So if we evaluate that polynomial, this derivative of the polynomial at 1, right, you can see the nice thing about modeling it in terms of x minus 1 is that all of these terms go away, just like they did before when we were modeling at 0. But now these x minus 1 terms turn into 0. So C1 is the value of P3 at 1 is C1. And we want it to match the value of the function, the derivative of the function at 1. So that's f prime of 1, right? And so that's just telling us now that C1 is equal to E, okay? And I just realized that I did this wrong, right? So I don't want f of 0, I want f at 1, right? So that should be E, all right? Because we're going to need to model around the E. We want the value of the function at 1 to match. So we want the value of the function at 1 to be E. And then the value of the first derivative is also E. And then we can keep going. We want to find the second derivative. And we'll end up with 2c2 plus 6c3 times x minus 1. And if we evaluate that second derivative at 1, okay, we'll get 2c2, which has to be equal to, here I'm messing up here, this should have been E as well. All right. All right, so that we want that to be E, which is the value of the second derivative at 1. Okay. And so that tells us that C2 is equal to E over 2. Right? I want 2C2 to be equal to E, so C2 equals E over 2. Okay. And then third derivative, we want those to match because we want a third order polynomial. So the third derivative of the polynomial is 6c3. And then the value of the third derivative at 1 is equal to 6c3, right? 6c3. And we want that also to equal E, which is the value of the third derivative of the function we're trying to model. So that's going to give us that C3 is equal to e over 6. Okay? So now we have the values of all the constants, which also, I left that out, but C0 will also be e. Okay. And so our polynomial, P3 of x, is going to be e plus e times x minus 1. Right? I'm just plugging the constants into the general polynomial that we're trying to model. And then we have e over 2 times x minus 1 squared plus e over 6 times x minus 1 cubed. Okay, did I copy that all right? Looks good. Okay. All right, so we're just plugging in those values for C0, C1, C2, C3 into the polynomial that we were trying to use to model e to the x. All right, that's the long way. Now let me give you the formula. Okay, it's very similar to the one I just gave you for modeling around x equals 0, only now we're going to, it's going to be f of a, right, plus f prime of a, right, times x minus a, okay, and the next term is going to be f double prime at a over 2 factorial times x minus a squared plus the third derivative of the function at a over 3 factorial times x minus a cubed, and so on, right? And so in general, it's the nth derivative at a over n factorial times x minus a to the nth power. Okay, and then we'll just use that. So I have one more example, and just using this formula. So I'm going to model 3 different polynomials. All right, of degree Taylor polynomials of grade 2, 3, and 4, approximating. Now we're doing natural log. Okay, natural log of x instead of, okay, we've got a new function, so that's good. We want to model near x equal 1. All right, so let's first of all look at f of 1. F of 1, natural log of 1, is just asking e to what power is equal to 1, so it's got to be 0. So f of 1 is 0. All right, so now let's look at the derivative of natural log. So the derivative of natural log is equal to 1 over x, but I'm going to write it as x to the minus 1, just because then I can use the power rule to come up with the rest of the derivatives, right? So the second derivative of natural log is a derivative of the derivative, so I'm going to get minus x to the minus 2, just using the power rule. And the third derivative is the derivative of the derivative of the derivative, right? So we'll take the derivative of the second derivative. And so if I take, so again, I'm using the power rule, so I'll end up with minus 1 times minus 2, so I'll get 2x to the minus 3. And then the fourth derivative is going to be just the derivative of the third derivative, so I'm going to get minus 6x to the minus 4. All right, now I need to evaluate those derivatives at 1. So f prime at 1 is equal to 1. F double prime at 1 is equal to minus 1. F triple prime at 1, all right, I'm just putting 1 in for x, so I get 2. And the fourth derivative at 1 is equal to minus 6. Okay, so I've got all the values of the derivatives. And now I can just plug this stuff into the formula. So now it doesn't actually ask for P1, but I could calculate P1 if I wanted to. It's just going to be the value of the function at 1, which is 0. So I can just kind of leave that out. and then I've got the value of the derivative at 1, which is 1. So the first order polynomial, first order Taylor polynomial is just going to be x minus 1. Okay. Now, now P2 of x, okay, so again, the value of the function is 0. Value of the derivative is 1, so we just have 1 times x minus 1. And then the second derivative is minus 1, so we're going to have minus 1 over 2 factorial, right, because we're looking at this third term. Yeah, it's really the third term because I left off the first term because it's 0, right? So we have 1 over 2 factorial times x minus 1 squared. Okay, that's our second order polynomial. And the third order Taylor polynomial then will just basically be the same two terms here. So we'll have x minus 1 minus 1 over 2 factorial x minus 1 squared, but now we have to add in the third term, which is going to be the derivative of the function. So we have 2 over 3 factorial times x minus 1 cubed. All right, so that's our third order Taylor polynomial. And then the fourth order Taylor polynomial I'm actually going to write down here. So P4 of x, it's a little longer, of course. But the first three terms are going to be the same, right? So x minus 1 minus 1 over 2 factorial x minus 1 squared. And then we have, now I could simplify these, you know, I mean, this is just 1/3 and this is 1/2. So when I do that, I'll just simplify these since I know them. So I can actually take off the 2 factorial. Whoops, erased too much. All right, gotta add it back in. So because 2 factorial is 2, right? 2 times 1. And this 2 over 3 factorial simplifies down to this, right? This is, 3 times 2 times 1. So, oh my gosh. All right, let me rewrite that. Okay. This is 3 times 2 times 1, so the 2's can cancel. So I'll just get 1/3 x minus 1 cubed. Okay, and then I have to add in that last term. And the derivative, the fourth derivative is minus 6, and it's going to be over 4 factorial. And that's times x minus 1 to the 4th power. Now again, I could simplify this if I want to, right? Because this is 4 times 3 times 2 times 1. So these last 3 factors will cancel. So really it just comes down to being 1/4 times x minus 1. All right, so that's all I've got for you today. There's some discussion problems, discussion questions for you to work on. And I will see you soon.